In this video, I will derive the below 4 kinematic equations. Before I start deriving the equations, let me state some of the assumptions first. So in order for these equations to work, air resistance has to be negligible. Also, as you can see here, there's some acceleration component in the equations here. The acceleration has to be constant. So constant acceleration. Before I start deriving the equations, let me discuss some of the variable here first. So delta x is change in position, change in displacement. So x stands for displacement. So x is displacement. V stands for velocity. So v sub f is final velocity, v sub I is initial velocity. So v is velocity. And A is acceleration. And T stands for time. So delta T is change in time. Now, what's the relationship between displacement, velocity, and acceleration? Well, we know that acceleration is change in velocity over change in time. And we know that velocity is change in displacement over change in time. So if you have acceleration and you want to go to velocity, you have to integrate and go backward to get velocity. And if you have velocity, you want to get to displacement, you have to integrate, which go backward to get to displacement. Okay, now let's start with the first one. This equation here. V sub f equals to V sub I plus acceleration times time. So now start with the derivation. Or we call the plus the first equation. So if I look at the first equation here, you see in terms of velocity. So you are looking for velocity. How do you start with that? You have an acceleration here. So to go from acceleration to velocity, you have to go backward using integral calculus. So we start with this. A equals to change in velocity over change in time. So A equals to dv over dt. So we start with that. And that's the calculus form. If we want to write it in the form that's not calculus, we can write as delta v over delta t. Okay, so now A is delta v over delta t. And what is delta v? Delta v is just simply v final minus v initial. We will keep delta t the same at the bottom. Now, you can just rearrange the equation by multiplying both sides by delta t. So we have A times delta t equals to v final minus v initial, right? Add v initial to both sides. So you have v initial plus A delta t equals to v final. Now, just need to switch the side. So we have v final equals to v initial plus A times delta t. And that's exactly the same as the first equation we have here. Okay, so that's one way to derive this. We can also use calculus. Let's look at it from the calculus perspective. Using calculus. So if we use calculus, of course we have to start with this. A equals to dv over dt. So A equals to dv over dt. And let me just switch the side. So I will write dv over dt equals to A. Okay. So like I said before, if you want to go from acceleration to velocity, you have to use integral calculus to go backward. So I have to integrate this. So I have to multiply both sides by dt first. So dv is equal to A dt. If I do that, multiply both sides by dt. So dv equals to A times dt. And of course, I have to integrate both sides. I have to integrate dv to get v, to get velocity. So I have to integrate dv, and then of course I have to integrate this side. If I integrate one side, I have to integrate the other side. Now, what would be the lower limit and upper limit for this integrals here? Now, on this side, it is velocity. So of course, I have to integrate from initial velocity to v final, right? To final velocity. And on this side, we're integrating dt. So it's time. That means the limit of integration must be from time initial to time final. Okay, let's evaluate this integral. Integral of dv is just v. So we have v, evaluate from v initial to v final. And on this side, since we're integrating dt, so we will have this as t. So it's just at. And of course, we have to evaluate from time initial to time final. Okay, now we will put v final into v and v initial to v, right? And then subtract each other. So we have v final minus v initial is equal to, how about this side? I have to put tf into, right, t sub f into t, right? And then subtract, I have to put down t sub I into t. So I have at final minus at initial. And of course, we can keep this side the same. This side, we can factor out the a. So a times t sub f minus t sub I. Now, what is this? T sub f minus t sub I. It is delta t, change in time. So we can rewrite this as v sub f minus v sub I equals to a delta t. And just add initial velocity to both sides. We have v final equals to v initial plus a delta t. Also, that's exactly the same as what we have here that we try to derive. Okay, now let's go to the second equation here. Delta x equals to v initial times time plus half a delta t squared. Okay, so delta x is changing displacement, changing position. So now you have position function. You have a position equation. So how do we do it? Now this is displacement. And after deriving the first equation, you have velocity now. So to go from velocity to displacement, because we know that velocity is changing displacement over time. So you have to do integral calculus to go backward from velocity to displacement. So let's do this. So we have to start with velocity equals to change in displacement over change in time. I will do it here. So equation number 2, derivation. Velocity is change in displacement over change in time. And I will switch the order. Change in displacement, change in time equals to velocity. And of course, to do integral calculus, I have to multiply both sides by dt. I have only dx on this side, so I can integrate. Okay, before I integrate, we know that this is velocity. And I have velocity derived already for this one. So I can substitute this velocity, which is v initial plus a times delta t, into this v here. So I have dx equals to v initial plus a delta t. For the purpose of integral, we will leave as t for now instead of saying delta t. dt, so I substitute v final into this v here, v initial plus a times delta t. Now I can integrate both sides. In order for me to get position x, I have to integrate dx. Integrate this side as well, v initial plus a t dt. Okay, so what happened here is because this is position, of course, we have to start from initial position to the final position. And on this side, we're integrating dt. So we're integrating time. So the lower limit and upper limit must be related to time. So it has to be t initial to t final. So we can evaluate this integral now. Integral of dx is just x. So we have x, which is the position. Evaluate at initial position and final position. And on this side, we have, okay, so let's do this. This is just a constant because we're integrating dt. So we have to add t to v initial here. So it's v initial t plus, now there's a t here, so we have to add 1 to the power divided by the new power, which is a t squared over 2. And then evaluate at t's of I to t's of f, t initial to t final. So on this side, we just need to put in x final minus x initial is equal to, now we have to put in t final to t and also t initial to t, right? And then subtract each other. So we will start with v initial t plus, okay, so t's of f, so plus a times t's of f squared over 2 minus, now we have to put in t initial. So it's v sub I times t initial plus a times t sub I squared over 2. Okay, so now let's just keep this side the same for now. So we have final position minus initial position is equal to, okay, this side we can put the like term together here. So we will take out the bracket first. So it's v sub I tf plus a times t sub f squared over 2 minus v sub I times t sub I minus a times t sub I squared over 2. Now let's group the like terms together. So we keep the same on this side. So let's put the v sub I times t sub f minus v sub I times t sub initial, right? Let's put that together. Plus, now this one would be, okay, let me write this as half acceleration t sub f squared minus half a times t initial squared. Okay, so now let's factor out the common factor here. V sub f minus, so x of f minus x of I, final position minus initial position equals to v sub I. So v sub I times t final minus t initial plus half a times t final square minus t initial square. We keep this side the same. Okay, so, okay, how can we write this sign now? Final position minus initial position is change in position. Now, final time minus initial time is change in time. So I can write delta t plus, okay, so this one here, t final square minus t initial square. But we know that usually when we start the time is usually 0, right? T initial is usually 0. That's how we start. And if that's the case, this term will just be 0. And when this term is 0, we only have t final square. So think about this. Change in time is t final minus t initial. And if t initial is 0, so change in time is equal to t final minus 0, which change in time is just t final. So this is basically change in time. So half a change in time squared. Okay, so we don't need this. Now, this equation here is exactly the same as the one we try to prove here. Here, exactly the same. Okay, now, this is the calculus approach. Let's look at it from the graph. Okay, let me draw a graph here. Now, okay, this would be a velocity time graph. Okay, now, let's take a look at this. If there's no acceleration, then the velocity would be constant. So let's say here. So this will be velocity. Let's say this is initial velocity, and it's going to be the same as final velocity because this is constant velocity. Okay. But how about with acceleration? The curve will look like this. So this one is with constant acceleration. And at some point here, let's say here, so we have the final velocity, which is we have here. Because you have constant acceleration and velocity, final will be different from velocity initial. And of course, at the beginning, right, this is the time graph. So this must be t initial. And when you reach the final velocity, this point here, this must be time final. Okay. So now, let's take a look at this. Now, remember this. Velocity is change in position over change in time. So if you multiply both sides by dt, okay, we have dx equals to v dt. You want to get the position, if you integrate both sides, you get the position. You're integrating this. You're integrating v. Okay, so also think about this. What would you get if you integrate this graph here? You integrate v. So you're integrating the v function here. You are getting the area under the curve. So if you have a constant velocity, you only have this area here. This area here. So with constant velocity, your position, change in position will be just v initial times delta t, right? That's constant velocity. But you have acceleration. Since the acceleration is constant, that's why this is a linear curve. So you have to include the area under this triangle as well, under this area. And what's the area of this triangle? Well, we know the area of this rectangle is v initial times t final minus t initial, which is change in time. How about this one here? So let me write like this. So this one here is delta t. Now think about this. What would be the area of this triangle here? Okay, we know that the base of this triangle is delta t. It's the length of t initial to t final. So we need to know the length of this height here. What would that be? Now, since it's constant acceleration, right? assuming that on the first second, you increase by 2 meters per second square. Per second, let's say, right? You increase by that. It's acceleration, okay? Per second square. Okay. Second. You increase by 2 meters per second square again. It's constant acceleration. And the third second, you increase by 2 meters per second square again. Okay? So keep going. Okay, let's talk about only the first 3 seconds. What's the total of this? 2 plus 2 plus 2 is 6 meters per second square. Okay? Now you have 3 seconds here. Your acceleration is 2 meters per second square. And the time is 3 seconds. Then, how do you get 6? It's 2 times 3. 2 times 3 is 6 meters per second square. So, that's what you get. It's basically A times T. So, A times T. So, that is A times T. That's your acceleration over time. And of course, right? Over here, A times T is basically A times delta T. Right? Change in time. From 0 to T final. From time 0 to T final. So, what's the area of this triangle? We know the area of a triangle is half base times height. So basically, this is A delta T times delta T divided by 2, right? So it's the base delta T times the height, A delta T. So we have to include here. Plus half A delta T squared. So now, that is your position. Exactly the same as this equation here. So when you integrate the function velocity time, you get the area under the curve. Basically, this is a curve that you have to integrate. It's this one here. This is curve that you're integrating. And you get the area under the curve from T initial to T final. So same concept here. So that's how you visualize this equation here. Okay, let's talk about the third equation. This one here. Delta x equals to V final plus V initial over 2 times delta t. So the third equation. Equation 3. Again, to visualize this, I have to draw a graph again. So let's do this. This is the velocity time graph. Again, your initial velocity is here somewhere, let's say here. So that would be V initial. And of course, this one here is T initial because we start with time 0, right? That's why we start moving. Or maybe we start from here, even though the velocity, initial velocity is not 0, but we start counting from here. So time is 0. Okay, so let's say at some point here, you have reached final velocity. So V final is here. Then the corresponding T value, the time here, would be T final. Okay, so again, here, change in position over change in time is velocity, right? So if I want to find position, I have to integrate velocity. So multiply both sides by dt, I have v dt. I have to integrate dx to get x, the position. I also have to integrate velocity. So when I integrate velocity, basically I'm integrating this velocity function here. I will get the area under the curve here. If I put the limit as, let's say, T initial to T final. So I'm getting the area under the curve here. this area here, because the integral give you the area under the curve. Okay, so what's the area under this curve here? If we look at this curve here, like really look at this area here, right? Here, it's a trapezoid. What's the area of a trapezoid? It's upper base plus lower base divided by 2 times height. So what would be the upper base here? Is V initial. And what would be the lower base here? Is V final. V final. So of course we can say that, right? We can definitely just say that, okay, V final plus V initial already, right? Is the upper base plus the lower base divided by 2 times the height. So that is the height here. And this one here is change in time, delta t, right? T final minus T initial. So times delta t. So that's the area of this trapezoid here. So that's also the displacement. So I can always write this as same thing here. So this will be delta x, change in displacement. So delta x is equal to V final plus V initial, all divided by 2 times delta t. So this is exactly the same as the third equation here that we try to derive. Okay, also one more thing about this is that V final plus V initial divided by 2 is the average velocity. So we can write this as delta x equals to average velocity times delta t. We have to use average velocity. Now, normally, this distance, let's say from the math perspective, not from physics. So distance is equal to velocity times time. So in this case, it's displacement equals to average velocity times change in time. Because we have to use average velocity because the velocity is not the same all the time, right? That could be acceleration, basically here. Your velocity is changing with constant acceleration. So we cannot just use one initial velocity here because we're not really accounting for it correctly. So we have to use the average of the final velocity and the initial velocity. Okay, so that's equation 3. Let's look at equation 4. This one here. V sub f squared equals to V sub I squared plus 2a delta x. Okay, so here, let's start with the third equation that we have here, which is this one. Delta x equals to V final plus V initial over 2 times delta t. So let's start with this. Okay, so let's look at equation number 4. So we have, okay, we start with this. Delta x, the third equation, V sub f plus V sub I divided by 2 times delta t. Okay, but we need to isolate V final. So what can we do? From the first equation that we did, the proof, we know that acceleration is V final minus V initial over delta t. So over here, this one here. So let's utilize this. So we know that acceleration is V final minus V initial over delta t. Okay, so we have a delta t here, so I can isolate delta t here and then we place delta t here, because in this equation here, as you can see, there's no time component here, so I can take away the time. Okay, so this one here, I can just take, okay, so delta t is equal to v final minus v initial over acceleration. Okay, so I can replace this delta t into here. Okay, so next here will be delta x is equal to v final plus v initial over 2 times, this is delta t, v final minus v initial over a. Okay, let's simplify this. We know that okay, when you have, let's say, m plus n times m minus n, we get m squared minus n squared. So this case here, we get v final square minus v initial square over 2a. Because the denominator is 2 times a. Okay, now let's switch the order. So v final square minus v initial square over 2a is equal to delta x. Now multiply both sides by 2a. So I have v final square minus v initial square equals to 2a times delta x. Now add v initial square to both sides. We have v final square equals to v initial square plus 2a delta x. Okay, so here we go. This is exactly the same as what we try to prove here, the original equation here. Okay, let's look at it from the calculus perspective here. So using calculus. Now, we obviously have a position here. We also have acceleration, velocity here. We do remember from before that, okay, velocity is change in position over change in time. And acceleration is change in velocity over change in time. Okay, so let's rewrite in a different order. Change in position over change in time is velocity, and change in velocity over change in time is acceleration. Okay, now multiply both sides by dt, we have dx equals to v dt. And this side, dv is equal to a dt. However, we don't have a time component in that equation. So we want to eliminate the t here. So we should leave dv here. So basically, I have to rewrite that dt equals to dv over a. So I can replace the dt here. So I have dx equals to v times whatever dt is here, which is dv over a. And in this case, velocity and acceleration are both constants. So I can rewrite this as dx equals to v over a dv. Now, we have to integrate this to get the position. So let's do this. Integral dx is equal to integral of this side, v over a times dv. We're integrating dx here, which is the position. So the upper limit and lower limit must be now initial position to final position. On this side, we're integrating velocity here is dv. So the lower limit must be initial velocity. The upper limit must be final velocity. Okay, let's evaluate this integral here. So integral of dx is just x. Evaluate at initial position to final position. And on this side, well, v is the variable we're trying to integrate. So we have to add 1 to the power divided by the power. So which I have v squared over 2a. Evaluate at v initial and v final. Let's evaluate this definite integral now. So this side will be x final minus x initial is equal to, here we have v final square over 2a minus v initial square over 2a. So let's group this together. We have a common denominator. We have x final minus x initial equals to v sub f square minus v sub I square over 2a. And what we know is that final position minus initial position is just change in position. So I can rewrite this as delta x. Delta x. Now multiply both sides by 2a. So let me switch the order first. So I have to write, let's say, v sub f square minus v sub I square over 2a is equal to delta x. Then I can multiply both sides by 2a. V sub f square minus v sub I square is equal to 2a delta x. Now, add v sub I square to both sides. We have v sub f square equals to v sub I square plus 2a delta x. Now, this is exactly the same as what we try to prove here. This one here. Okay, so here's the derivation of these 4 kinematic equations. Hope you enjoyed this video. Don't forget to subscribe to my channel. Thank you.